Hello and welcome to this episode of our broadcast. I have in the studio with me Clinton, all the way from Nairobi. Clinton, say hi.
Hi everyone.
I have John, who's in Lagos with me. John, say hi.
Hello.
And I have Aloba. Um, Aloba, can you hear us? No. So I hope Aloba can hear us, but anyways, we'll fix whatever glitches we have. So it's a packed house today, and the purpose of today's session is Aluba has gone through the TinyML course, and he had a few questions. He shared those questions with me, and I thought, well, why don't we just come online and answer those questions? Because if one person has a question, it's more than likely that the second person has that same question. So as you watch along, please feel free to drop your own questions. So we'll start by answering Aluba's questions, but feel free to drop your own questions, and we will answer them as well. So for now, I will leave the studio. But while we do that, Clint, maybe you should just do an introduction of the Edge Impulse platform while I try to log into Edge Impulse, and then we'll start talking about the questions that we have.
Awesome. So, hi everyone. Just my introduction, Clinton from Nairobi. I'm an Edge Impulse ambassador. So, Edge Impulse is an MLOps platform for developing TinyML models to be deployed to edge devices, mostly microcontrollers. So, Edge Impulse allows you to collect your own data from your target devices, or even if you already have like some collected data from other sources, it has like a feature that you can upload your data, perform digital signal processing tasks, and even do machine learning operations such as classification, regression, and even anomaly detection. And it also gives you a chance to deploy your models to your edge devices without needing to write the firmware by yourself. So it has already some set of supported development boards, such as the Arduino Nano 33 BLE Sense and others, that when you want to build your TinyML application, what you just do is you just train the model on the platform, and you port everything, including the firmware, to run the machine learning model to your target edge device. So that's just a brief introduction about Edge Impulse.
Okay, thanks, Clinton, for the intro. And I think Aluba is back, so let's add him to the stream and see
Awesome.
if we can hear him clearly. So, hi, Aluba, can you hear us now?
Yeah, I think I can.
Okay,
Can you hear me
fantastic.
too?
Yes, we can hear you. So, thank you for joining us today, and thank you for completing the course. One thing I can say is completing online courses isn't easy. Yeah, it takes a bit of motivation to start and go through to the end. So, um, why don't you introduce yourself and just spend a few minutes talking about why you took the TinyML course and what your experience was?
Yeah, okay. My name's Alba, and currently I work I program I work for Primalda Design Zone Systems, and I work on hardware and microcontrollers, and I write the hardware. I design the hardware and write the firmware. So I my motivation for taking the course was because most times um I'm always like, okay, I've made so many modules about TinyML and machine learning and AI. So I felt like, okay, what was really happening in this space? So that was it. And the course was a soft entry into the machine learning AI space. So I decided to take the course. It was a really nice journey. I the delivery was okay. I I get to learn all the things. Yeah, that's it. Thank you.
Okay, thank you for that. So I know you mentioned you actually sent me an email and you mentioned a few things that you needed some clarity on because the interesting thing is Alba told me when he started the course, he sent me an email and said he was going to take the course. And I said, okay, lovely. Here's what I want you to do. As you go through the course, make a list of questions that you have. And then when you're done with the course, send me an email with all those questions and we will try to get a way to answer them. So we're going to start with the first question, which is feature extraction. Um, so I don't know, Alba, do you want to provide some additional context around what you'd like us to talk about in feature extraction?
Yeah, I think the thing about the feature extraction is after getting the data and how you were able to, let's say you taking so much amount of data and you being able to just extract, let's say, few features of it, let's say one or two or three features without having great accuracy. So it's something that I feel like I didn't understand almost immediately. So I feel if anybody could share more light on it, that would be okay.
Okay, great. Um, so, Clint, is that something you want to talk about immediately? Let's talk about feature extraction.
Yeah, sure. I can touch on that a little bit. So feature extraction usually like a very it's a very important like step when it comes to training your machine learning models because as we said like these machine learning models should just go depending on what it has been given. So for you to get like the best performing model, you really need to know how to select the best features. So and sometimes like it's obvious like you don't want to train like your machine learning models directly with the raw data that you have collected. So you must first of all convert it to a form that a neural network can better understand it in case you are using a neural network for your application. So when choosing your features for training your model, you really need to know like the best features to choose. And sometimes usually very difficult. For example, if you are not coming from background with digital signal processing, because like when you're working with something like audio, you're going to get things like MFEs and MFCCs, which sometimes you are not quite sure about which one works well. Sometimes when you're dealing with accelerometer data and vibration data and the rest, you're going to meet like a lot of features that you sometimes you don't have like that much knowledge. So the good thing about a gym pulse is that it can give you like it can always suggest to you like the most important features. There is a checklist that you can checkbox that you can always check it, and it's going to give you like the best feature for that particular data that you have selected. It's going to give you a list so that if you if you choose, you can just remove like the features that that you think are not important to your machine learning model. Another good feature is that gives you the capability of using like your own custom digital signal processing block. That's when maybe you feel that you have like much knowledge of what you are currently doing. So it gives you like the ability to be flexible enough so that you can also like use the features that you think works best for that particular data. Yeah. So John, Robert, back to you. Back to you, Robert. John.
Yeah, you are
Okay.
muted, Robert.
Sorry. Yeah, okay. I just realized I'm muted. So I was saying, interestingly, we were on um, another session, another Edge Impulse session just before this one. And someone asked an interesting question. And the question was, why do you have to do feature extraction when your ML model or your deep learning model is capable of doing that? And the reality is that your deep neural network is capable of finding features. That is actually the whole point of deep neural networks versus things like just your fully connected layers, right? So you have other types of layers that you can put in, plus your non-linearity, so your activation functions, and they will find your features. But it takes time, it takes a lot of computational processing. But then there's what we call subject matter expertise or domain expertise. And what domain expertise brings is the ability to say, these are the things that are important in this type of problem. And so you can quickly extract those features, and it reduces the amount of computation that your ML model needs to do both during training and during inference. Quick question, because I shared my screen, but I see some sort of pink overlay. Are you able to see it normally? Okay. So it looks like everybody else sees it normally, which is fine. All right. So I also shared my screen, and this is Edge Impulse. This is a project that deals with accelerometer data, or initial measurement units. And typically, a lot of the work happens around the impulse design. So there's the data acquisition, and in this example, you have accelerometer data, which you can see here. So it's a three-axis accelerometer, and as it gets moved around, you can see the data that gets captured. So this is time series data on three axes, and um, when you pass it into your ML model, it might not be the easiest thing for the model to extract. It will eventually extract it, but you need lots and lots of layers, lots and lots of epochs of training, right? But when you then come to your impulse design, in that you're able to set some parameters, particularly on edge impulse, and then you're able to do your feature extraction. And that this is the feature extraction block that it was talking about. This is your spectral analysis, and then you pass it to your classification model, your Keras model. So when you look at the spectral features themselves, you're able to see what gets extracted when that spectral analysis happens. You're able to see examples of the raw features. You're able to see this is your digital signal processing, this is your frequency domain, your spectral power, because you extract a few things out of it. And you can see that from these parameters. And once you save the parameters, you're able to generate your features. And when you generate your features, you have a bunch of features. I can skip that feature generation part, but you have a bunch of features. And when you visualize, what you're trying to see is, even before I get to my ML model, will I be able to train a model that can accurately separate the different types of, or different classes of motion that I want that model to be able to classify? And what you see here is that, based on, I have four classes here: circle, idle, left, right, and up, down. And you can see the different colors. So circles are clustered around here. So it's easy to see that circles are different from up down motions. The green is my left right motion, and then we have idle here. So it turns out that this particular feature extraction actually found features that separate these things very well. Now, while I am viewing these things in 3 dimensions, note that there are a lot of features here, and how you find that out is you can plot other things here, and when you do that plotting, it helps you to decide whether or not to go with those features. Now, the interesting thing about this particular project is that I have two different models, and you'll see that when you go back to impulse design, there's a classification model, but then there's an anomaly detection model. And the features here in the spectral features, what they help you see is that you're able to classify these motions. You can separate them properly, and so even when it comes time for your anomaly detection, if you work with these three features, you'll be able to detect anomalies pretty well. So yeah, that's it with feature extraction on my side. So just a second, come up with the next question. So the next question was about epochs and loss functions. So Clint,
Yeah, sure. So about epochs and loss functions, so like basically epochs usually refers to like the number of complete training cycles that you train your model with. So the thing behind epochs is that you want to minimize like the error when you're training your model. So you just basically need to know that when training your model, especially neural networks, they usually call like something called like back propagation. Back propagation basically means that you're trying to reach like the global minimum, of which it's some of which usually like zero. So first of all starting with like random weights with like very big numbers, and you try to iterate till you reach zero, until you reach an error of zero. So the thing behind that is that when you want to reach zero, you are usually required to increase the number of training cycles. That means that you are supposed to increase the number of epochs. But when you maybe due to some limitation such as compute access to enough computing power, you might not be able like to reach the global minimum, but you must at least try as much as possible to reach like the global minimum is usually like zero. So how we usually determine like the method to reach the zero, how we usually determine like how do we move to zero, we usually use something called like a loss function. So a loss function is just like some sort of a matrix that shows you like how do you get the value that you're trying to reduce. So there's a lot. For example, if you can check here, maybe you can open the expert mode. Yeah. So most of the time when you're using like the Edge Impulse platform, you might not really want to know like the loss function that you're using if you're not an expert in it. But when you're an expert and you want to take full control of your project, you can always like get into the Keras expert mode, whereby you're going to be given like the raw Keras the raw Keras code, Python code that's running under the hood of Edge Impulse, whereby you can always choose the type of loss function that you are using. So in this case, you can see that you are using like a categorical cross entropy, which usually used for classification most of the time. When you want to classify maybe more than two classes, there are a number of other loss functions such as like the binary cross entropy, when maybe you have like two classes that you want to separate. So for example, in this case, we have circle, idle, left, right, up, down. So if you could be having like only two classes, you could maybe have used like the binary cross entropy. And if you are working on regression task, there are also like other loss functions that you can always try out, such as the mean squared error and mean absolute error. So advice on this usually like most of the time you want to use like a base like a loss function. It, what I mean by a loss-based function is that a loss function that has been proven maybe by research work. If you don't want to stress yourself much, you just use like a loss function that has been used by maybe a research paper to produce like some good results, and try to replicate it on your in your application. So if you see like you're not getting like some good result faster, you're not getting to the global minimum faster, maybe you try another loss function. Yeah. Thank you, Aloba. Thank you, Robert. Sorry.
yeah, thanks, Clint. That was really good. So one thing that Clint said, which is pretty important, is there are a lot of things going on with machine learning, and the best way of knowing what to do is just finding a paper. So there's lots of research going on, lots of data scientists doing work, and you can always just go find a paper within the problem domain that you're trying to fix. Because part of the problem with machine learning is that there isn't one equation or one formula or one function that works for everything. It's usually a case of like, we've tried this, it didn't work. We tried this, it didn't work. But we noticed that when we tried this, it worked on this type of data. Now, if you take that solution and apply it to another type of data, it might not work, right? So you need to, there are some things that are generally good, but they might not be the best for that problem domain. So you can always start with, oh, I know that this thing is generally good. And you see that example here where they just go with the Adam optimizer, which is what you have here, and then they go with a default learning rate, which you can change if you want to, you know. Um, Now, if you've read a paper that talks about another optimizer for the particular problem domain that you're dealing with, you can go ahead and try it and see what happens, right? So that's it with things like loss functions. And then the epochs, of course, is the number of times, like Clint said, that you go over your training data. And the more you go over your training data, the more you carry out that process of reducing the loss using your forward propagation and your backward propagation. So let me bring up the next question that we have. Okay, it's a good one. So the next question is on the F1 score.
Oh, thanks you,
Are
Robert
we
John.
are we are we going to are we are we trying to predict Formula One results before it actually starts? Don't mind
Um,
me.
yeah, so that's a good one. Um, so yeah, Clint, tell us about scores.
So like the F1 score is just one way of evaluating your model. After training your model, you might want to like know how it performs on a test data, because like when you test it with the training data, most of the time it gives you like a very good accuracy. And there are a lot of model evaluation metrics. We have the most commonly used like the accuracy, but there are other ones such as like precision and recall. But sometimes maybe you have like sometimes you first of all, when choosing, like before even start training like your machine learning model, you must know also like what you are really targeting. Sometimes accuracy might not be like the best metric for you, because maybe sometimes you might be having like an imbalanced data set, which will give you, of course, like a very high accuracy. For example, if you are having like two classes that you are training on, let's say like you are having like a classification problem, you want to classify between like a normal working machine and a faulty machine. You might have like a lot of data on the class of like a normal working machine and less data um, on the default on the faulty machine, on the faulty machine. So maybe the distribution might be around 80-20. If you use accuracy and say like everything is good, you're going to get like an accuracy of 80%, but that isn't like a very good like evaluation of your model, because it's like a completely wrong model. It's completely misguiding you, because it will just take everything as normal. So sometimes you might want to get into the specifics of maybe you want to use another metric such as like a precision and recall, and maybe you have trained like two machine learning models. One has like a very big precision, and the other one like has like a very high recall. So F1 scores usually come to our savior here, because like how do you decide like to choose between precision and recall? So we usually use like the F1 score to help us there, because like the F1 score is usually like some sort of a harmonic mean between like the recall and precision. So it balances like the recall and precision and give you like one score that you can use to evaluate your model. Yeah, thank you, Robert.
Okay, thanks, Clint. So obviously we're going to skip all of the mathematics that goes into computing that. It's available online, it's available in the slides. The whole point of the F1 score and all of the other evaluation metrics is just for you to determine how good your model is. And the starting point usually is the confusion matrix, as you can see here. And what is important here is that you can see that the overall model accuracy is 99.2%. But you can see that there's a particular class that doesn't get up to that 99.2%, right? And this is a relatively good model. You can see, so the green here is where you have your true positive, where what was predicted exactly matches the ground truth. For three of the classes, they are correct, but for this circle, 96.6%, if you want to round up to 97, that's fine. 97% of the time, the circle is accurately predicted, but there are times when it is predicted as a left-right motion, right? So what you see is for the circle, the F1 score is 0.9. For this particular class, the F1 score is 0.98. And then for the left-right versus idle and up-down. So what it means is that this model is pretty good. It could even be it could even have some overfit, right? But you'll need to go check that out later on. But based off of the evaluation data, you can see that idle and up down have a pretty good F1 score. So everything is really just it revolves around your confusion matrix of saying what is the quality of this model, because every model really just spits out something, right? It's now a question of how useful is the model, or as they say, every model is wrong, some are just useful. So let me go on to find the next question. Okay, so this is another good one. So it's about activation functions.
So thank you, Robert. So activation function usually like just a way of usually first of all used in neural networks, and usually just a way of like finding like the best neurons, like only neurons that make sense to the model. So like the best neurons, the neurons that make sense to the models are the ones that are going to be fired into like the next layer. So in a normal neural network, you'll find that you have like a hidden layer of a lot of layers, sometimes like a very big. And if you keep in mind that you want to use all the neurons, sometimes it's usually like very hard, because at the end of the day, you are going to have like a very large model with some neurons that don't even make sense sometimes. So activation function I usually use to know like which neurons like really make sense to this model. So when a neuron is activated, usually activated by an activation function, I can't just say that. And the activation functions are usually like very many, depending on your task. And again, here we'll just go back to what we have discussed previously, that you want to go back to like a base paper, a paper that has showed like a particular activation function performing very well for a certain like type of model. So most of the time you'll find that for image classification task and other tasks, you find that ReLU is usually like the most commonly used activation function, but there is a ton of other like classification function. If you can see like Robert's screen, it's a list of very many activation function. You might want to experiment like which one works best for you, but as a starter, it's really good to go to the base and use like activation functions that have already been proved to be working very well. So you realize that most of the time the activation function used for the hidden layers is usually like very different from the one used in the final layer, depending on your task, whether you are, if it's a classification task, are you dealing with two classes or are you dealing with more than two classes? So those are the things that you usually want to put into consideration when you are choosing like your activation function. But the principle is that you usually want to go back to maybe a base research paper that has proven like a particular activation function working very well for a particular application. Thank you, Robert.
Okay, thanks, Clint. So I will also add that the activation functions are not all the same. So first of all, like Clint said, what they do is they introduce a non-linearity. So recall, and let me come back here first, and then come back to the simple one. So recall that what you have in your neural network is a bunch of layers, and every layer has neurons, right? So here we have an input layer with 33 features. What it means is that recall where we had this XYZ, there are 33 of them that get passed in at the beginning of our neural network. Now, at the next layer, there are 20 of them. So every one of these 33 will be multiplied by a random weight. And then it will be output. And then that output will be the new input here for these 20 neurons that we have. Now, you will also repeat the same thing. These 20 neurons will be multiplied by weight. There will be an addition of a bias, and then they will end up here. So without an activation function, it becomes a linear operation, meaning that the output here just gets passed into, then multiplied by a new weight and then a new weight. It doesn't really change anything. So the activations, what they do is they kind of constrain the output. And that is where the choice of the activation function depends on the constraint that is introduced on the output. So if you take a sigmoid activation, for example, the equation is here. It constrains the output to a range between 0 and 1. If you take something like a hyperbolic tangent, which is called the tan H here, it will constrain the output to between -1 and 1. If you take a rectified linear unit, it will change every negative output to a 0, but it will leave the positive output the way it is. So they have different effects on the on your output, but they also have different computational costs. So you have to think about the cost of the computation depending on the size of your model. Now, in TinyML, we tend to deal with really small models. But do not forget that one of the things that you worry about in the end is your inference time. So if you have an expensive model, then the inference time starts to go up. So while you're thinking about your activation functions, it's not just a very simple case. One is some activation functions have been proven to work well. Yeah, okay, that's a good question. I'll get to that. So some activation functions have been proven to work well within certain problem domains, but then you need to decide for yourself whether the quality is worth the expense in terms of your processing power. So I can't remember whether I wanted to add anything else in terms of activation functions. All right. So before we continue with Clint's questions, there's a question here that I want to put up, which is, can Edge Impulse allow for sensor fusion, and what boards are currently supported? So it's two questions. Clint, do you want to go for it?
Yeah, sure. So Edge Impulse completely give you the ability to try out sensor fusion. Like sensor fusion is usually like a very good technique when, for example, you have like very many sensors and you want to do like maybe you want to classify something, or it's a classification or regression problem. So it's actually like a lot of applications, and for you to be able to perform sensor fusion, you just need to have like multiple sensors, more than one sensors, and sometimes you don't know the relationship between the data that you are collecting. So sensor fusion usually give you the ability to provide like give you like the best combination for your particular problem. So for example, let's take a use case of whereby you want to detect, for example, whether you are in a house or you are outdoor, and you have like two sensors, let's say the temperature and the humidity sensors. So you can just collect the data, the temperature and humidity data, and temperature and humidity data that you have, upload it to the studio, and you are going to find like the best combination that can enable you know whether it's a room or not a room. So Agimpass completely supports sensor fusion, and in terms of the boards currently supported, it can support typically any type of board. It just depends on the sensors that you have. But of course, there are already like some development boards with multiple sensors embedded on them. For example, the Arduino Nano 33B license, among others, that you can easily get started with when you want to try out like some sensor fusion functionalities. Yeah. Thank
Okay,
you, John.
thanks, Clint. So, yeah, like Clint rightly said, I brought up this screen because it shows you some boards, but it's not an exhaustive list. There's actually an API, and this is API and SDK reference. There's an API that you can call to pass your sensor data, and that data will end up in your data acquisition, separate from your devices. So if you come to data acquisition, you can push data from your code and it will end up here. And then you can split it into training and test and stuff. There's an API for that. Now, what you then need to worry about is from your development board, can you write code that will just call the API and pass the data across? That's really all you need to worry about. Now, even if you're dealing with boards and you want to use something native, for example, here it shows the Arduino Nano 33 BLE Sense, but it turns out that you can run the same because they just give you an Arduino sketch. What you need to know is what is on the Arduino Nano 33 BLE Sense and how is it different from the board that I have right now. And one example is I've taken the sketch for the Nano 33 BLE Sense and I've run it on a Nano 33 IoT. The difference is that the Nano 33 BLE Sense has a 9-axis IMU. The 33 IoT has a 6-axis IOU, I believe, IMU. And so all I had to do was change the library from using the device driver for the Nano 33 to the one on the IoT, and then it just ran. I didn't have to do anything different. And that's what you actually see when you come to devices here. So you see that I have a Nano 33 IoT that talks directly to Edge Impulse. So you can technically run it on any development board as long as you're just able to write code, generate like a JSON and push it across. Then The next question is, how do I deploy a model from Edge Impulse to a dev board? Again, there are so many ways of doing it. So there's a deployment section. You can get a C++ library, which typically is what you want to use for your production purposes. There's an Arduino library, which you can use if you're using Arduino boards. There's a something for STM32s. There's one for RT and WebAssembly. And they actually also let you even do deployments directly to Raspberry Pi. So you have a Python version that you can just take and work with. There's example code for that. So there's deployment to all sorts of things. There's also like a live classification, which will let you detect any device. So if I've got any of my boards connected, this will give me the option. Well, I have to connect the board and then run the firmware on the board. But then it will let me detect the board. It will find all the sensors on the board. So if I connect a potenter, for instance, it will ask me whether I want to use the microphone or whether I want to use the IMU or whether I want to use the camera at this point. And then again, depending on the project, and then I can start sampling, right? So yeah, that's the answer to deployment from Edge Impulse to dev board. So let me just find the next question from Aloba. So the next question is actually about MFCCs.
Okay, so I'll go first on it. So like MFCC is a way of extracting features on audio signals before like feeding them to your machine learning models. So before even going to MFCC, you must know like there are very many types of features that you can extract from an audio signal. And some of the common ones that you can also find from the Gimpal Studio by default are usually like MFCC and MFE. So if you feel that you may want to try maybe other types of custom digital signal processing blocks for your audio implementation, you might import it. But those are the most commonly ones that are currently available on the Edge Impulse platform. And the Edge Impulse platform will also give you like it will always suggest you like the best one to use by highlighting like some sort of a star, a gold star on it. Maybe if you don't have like much expertise knowledge on that field. So MFCC usually like basically a way of like getting meaning out of like audio signal. So as the name suggests, MFCC stands for forwards, mel, frequency, septal coefficients. So basically, what happens here is that when collecting your audio, usually collect it in like some sort of like time domain, but you might not see all the you might not have like all the you might not see like all the features that you have on your audio by just analyzing it on a time domain. So you convert it first of all to a frequency domain, but also like frequency domain might not help you much. So the human ear has usually like a range of frequency in which it can understand low frequencies and high frequencies. So what MFCC does is that it tries to give your audio like a way to interpret like the signal the way a human being understands or interprets audio signals. So it chunks them into some coefficients. There are usually like some defaults that you might want to use, maybe 13 coefficients, 20 coefficients, and the rest.
Did we lose Clint?
So at the beginning, I told Clint to pray to the God of the internet. Um, and so I was just checking whether it was my own internet that went down. But yeah, it looks like it's Clint's side that went down. So while we're waiting for Clint to come back, let's try and continue with MFCCs. So as Clint was saying, the raw data capture for sound is okay. Clint is back. Clint, welcome
Oh,
back.
sorry. Oh, sorry,
Okay.
sorry. It was my network had some issues, but I'm now back. Yeah. So I was just concluding. So if you have like expertise and knowledge on audios, you can always try to tweak some of the coefficients that you have. But if you don't, you can always use like the default ones that are there. So what you might want to know is that when you are using like voice data to training your model, MCC is usually like a very good fit for that particular application. And when you are using like now voice data, you might want to try out like MFE, which usually like spectrogram representation of the audio signal. But you can always try out which one works best through like some experimentations before settling on one. Yeah, thank you, Robert.
Okay. Thanks, Clint. Um, so I think the thing to note with speech and sound is that it's pretty complicated, and you can see the representation up here where you're dealing with frequencies, plus there's also the question of power. So for example, this is an unknown sound, but since I have four categories, I can actually scroll down to if I have so many unknowns. So what's the data? Oh, I have a lot of. Okay, I get it now. Sorry, I will need to do a lot of scrolling to find something that is not an unknown, but that is a no. Looks like I won't find it here. Uh, so I wanted to show you what some audio looks like, some other audio looks like, but basically what you're dealing with is this. Now, could you process this in a neural network? Yes, you could, but you'd be dealing with a lot, right? So you probably would have to deal with things like a recurrent neural network and things like that because it's a time domain you're going across. Um, but when you do your digital signal processing and you end up with your MFCCs, you end up with this image. And now it turns out that we've had more advances in the image classification domain for machine learning than we've had for like speech and other things. Well, over the last 2 years, we've had more of the speech, but in the past, we had more on the computer vision side of things. And the interesting thing about this is that it looks like something, it looks like an image, even though it's wider, but it looks like an image. And it looks like something that you could treat as an image, right? Once you have this MFCC. And that's what you see in the impulse, where you go from your time series to your MFCC and then to a neural network. Now, when you go into this neural network, what you notice is that um, you're now dealing with convolutions because when we deal with images, we tend to deal with convolutions. The difference now is that as opposed to a normal image where we deal with two-dimensional convolutions, here we're dealing with a one-dimensional convolution. And what happens is, I'll come back here. In a two-dimensional convolution, you have a kernel, usually a square kernel, 3 by 3 or 5 by 5 or whatever, that will go across using a stride, and then it will come down and then go across again. So that's what makes it a two-dimensional convolution, where it's convolving the image across 2 dimensions. But because this is speech, we use a one-dimensional convolution. What that means is that The sliding window only slides from the beginning to the end. It doesn't come back down. So it's one long window that slides across. And as it slides across, it extracts features, it learns features from that. And so the benefit is that you're able to use convolution to extract your features and then carry out your classification. Okay, so we're almost at the top of the hour. I believe we're at the last question now. Just a second, please. So our last question is two questions actually: convolutional neural networks and sensor fusion. Okay, Clint, which one do you want to go with first? So I know where to jump to.
So I think I'll start with the convolution neural network. So convolution neural network is a way of analyzing data that is in a spatial domain. Most of the time when we use tabular data, we might want to use like some normal classical ML algorithms or just basic neural network. But when you're working with convolution, with a spatial data, for example, an image or an audio, just the way like Robert has talked about, we may want to use like a convolutions. So convolution, what help us is that it help us like to extract some features. So maybe Robert can just share like the convolution neural network block on edge impulse that you might want to expand on more. So you might want to use like the default network, convolution neural network that have been given by Gimpulse, or you might want also to go to the Keras model to define like your own convolution network. So basically, you just set like the number of filters that you want to use, and the size of the kernel. So the kernel size is basically like a matrix that extract features on a, it's some sort of you have like one big image and you are passing through a kernel. A kernel is basically a matrix that multiplies like each pixel with it to give you an output. So for this case, for example, we have like 32 filters with a kernel size of 3 by 3, and we're having a ReLU activation function. So you might want to have as much number of CNN networks that you might want, CNN layers that you might want, but it also comes to trade-off of like how much memory do you have. Of course, if you have like very many, you might find it difficult to run on a constrained device such as a microcontroller. So you might want to use like a basic one with only a few number of layers. Yeah, I think I'll leave it from there, Robert.
Okay, thanks, Clint. So basically, from the beginning, you would have started with a dense neural network, and a dense neural network just uses your dense layers. A convolutional neural network adds convolutions to your model. In this case, we have convolutions, which is defined by convd, and we also have pooling. And there are different types of pooling layers, but in this example, what we have is max pooling. The convolutions will extract features, and the pooling will highlight the features that we want. Now, the kernel itself, like Clint said, this is going to give you a 3 by 3 matrix. You're going to have 52 of them. So what you're going to have is 32 windows that will slide over the image. But each of these 32 is a 3 by 3 matrix with randomly initialized numbers. So part of the training process is also adjusting the numbers inside of these kernels or these filters that we have. As they go about doing their job, they're extracting all sorts of features from the image. Typical example that you hear is, some of them might be finding, is there a vertical line? Is there a horizontal line? What sort of edges exist in the image, right? That's what the filters do. But filters can also do all sorts of things, and that all depends on your pooling. Some of them will sharpen certain features, some of them will blur certain features. They do all sorts of things, but they learn to adjust because in the end, you still have a classification at the end, right? So your back propagation will say, hey, you know, you are far away or you are close enough, hot or cold, and then the filters will get adjusted. The weights within the filters will get adjusted for that. So simply put, really, once you know what a deep neural network is or a dense network is, your convolutional network just has convolutions and pooling layers before you get to your dense. In this particular example, we flatten after we do all of our convolutions and pooling, we flatten, and then you can ignore the dropout. The dropout is just to avoid overfitting. And then we get to a dense layer. Now, you can have multiple dense layers. And here you can see that, for example, we have a softmax activation. So this is just to deal with the number of classes that we want to be able to predict, right? Which is defined by classes here. So that's your CNN. So, Clint, we have 4 minutes. Do you want to add a little bit about sensor fusion?
Yeah, sure. Because we already talked about it, just to add on it is that like sensor fusion, it's not a must you have like different sensors. You might also have want to have like the same sensors to get like a proper representation of your environment. For example, you might want to have like two cameras to give you like a particular degree of view, maybe. And the traditional approach of doing sensor fusion was through like some hard-coded algorithms such as like the Kalman filters and the rest. But now you can do sensor fusion using like neural networks, and it's a feature that you can try it out using like the Edge Impulse platform if you don't have much knowledge on ML and the rest. Yeah, I think I'll only add that on sensor fusion.
Okay, thank you so much, Clint. So, Aloba, I don't know whether we were able to address all of your questions or whether you'd like a second session.
Yeah, it feels better. I feel like I'm living in it better. I can I tend to understand some of that stuff better. So
Okay,
thank you.
fantastic. So, we don't have any questions in the comments. We had two questions and we thankfully addressed them early on. So, we're almost at the top of the hour. I would like to say a very big thank you to everyone who tuned in, as well as to everyone in the studio, Alba, John, Clint. Thank you so much for taking time out to join me in the studio today, and enjoy the rest of your day.
Thank you,
Thank you,
John.
Robert. Bye bye,
Bye.
everyone. Yeah, thank you.
Thank you, all right.